which is, there's also another kind of digital manufacturing technologies for ceramic elements, but this is very suitable for bigger or larger scale fabrications, and it maintains the properties of the ceramic materials and improves the speed of the process, and so that's very suitable for large scale. In this process, we have a printing nozzle that is depositing some amount of material, and while is it moving, so that creating these printing lines, and all the set of the printing lines that are on the same height are the printing layers. So that our hypothesis is that the material is going to behave as an orthotropic material with different mechanical properties with the X, Y, and Z direction. In the X direction, we have a continuous material because it is the printing direction. In the Y direction, we're going to find these vertical joints between the printing lines. And in the Z direction, the horizontal joints between the printing layers. So that our research questions is if actually the material behaves as an orthotropic elastic material, and to what extent it behaves like that. And also, we're going to carry out some ultrasonic or non-destructive tests to see if there is a direct relationship between the mechanical properties and the speed of the ultrasound propagation for this material that could serve as a basis for developing a quality control protocol non-destructive. So this is the methodology through the manufacturing of the test piece. We're going to carry out mechanical tests, compressive and three-point bending, then some microstructure tests through X-ray tomography, and the homogeneity test will be the ultrasonic ones. So that we, with all of this, we're going to understand better how the material behaves, and also to maybe try to develop that protocol non-destructive. And the further work will be to create the finite element model for this kind of fabrications. The printing setup is like this. We have a 5-liter pneumatic tank controlled by an Arduino and mounted to an ABB robotic arm. And with all this software, we created kind of a new workflow, very friendly with the designers and all the digital fabrication purposes. We manufactured three different batches, and by the combination of 2 printing materials and 2 different printing nozzle diameters. So that we use the white clay and red clay, the 2 of them reaching a maximum sintering temperature of 180. And with these printing parameters. This is one like those batches look like. We have 3 different compressive strength test pieces and 6 different three-point bending test pieces. For all of that pieces, we carry out the ultrasonic test for the longitudinal speed and the indirect speed. And all those tests were carried out also for molded test pieces to compare the 3D printed pieces with the non-3D printed ones. So we can see in the mechanical test that the discontinuities caused by the 3D printing process create weak planes for the material to break through, These are the horizontal joints between the printing layers and the vertical joints between the printing lines. And we can see a more irregular break here in because we have a continuous material. Regarding the results of the compressive strength, we see a very big dispersion of the results for the X, Y, and Z direction. These are the 3 batches that we manufactured, but we can see a clearly differentiated behavior of the material. If we take the X direction as 100% compressive strength, we can see this behavior for X, Y, and Z. We see that for the 3-point bending test, the behavior is more different, it's much different. If we take 100% for the X direction, we see that the direction in the Y direction, the resistance in the Y direction is almost a third part, and almost the same for the Z direction. Even the solid test pieces are weaker than the test pieces than the 3D printed ones in the X direction. And these are the results for the direct ultrasonic speed that we see a very flat or a very similar behavior for the 3 batches. This is the batch A6, B6, and B8. And we see a very similar behavior. Looks strange because even this material is different from these 2, or even these 2 have the same nozzle diameter, but different. For this one, the ultrasonic speed is very similar between the 3 batches and very similar in the 3 directions, X, Y, and Z. We observe that the ultrasonic speed is always the same. If we compare the results with the tomography, we find that these cracks that were produced during the drying or sintering process cause this loss in the compressive strength, but not that much, because we are supposed that these cracks get close with the compressive strength. But regarding the flexural results, these cracks do produce a huge loss in the tensile strength, so that this huge difference between the X, Y, and Z. The thing is, it's logical to think that the ultrasonic speed in this direction is faster than in this one, in the Y, because the sonic wave will find this crack in his way. But it's strange to find that the Z direction, which is this way, in the tomography, we find a very homogeneous material, but it's the slowest one. So that our conclusion is that yes, both the flexural and the compressive strength shows similar or at least orthotropic behavior for the three batches, and that we observe a loss in the compressive strength for the direction Y, 24 to 51%, and 69 to 76 in flexural strength. And for the Z direction, 5 to 20 decrease in compressive strength, and 46 to 63 decrease in flexural strength. And for that purpose of finding a non-destructive protocol of quality control, even if we found that the ceramic shows the orthotropic behavior in terms not only for the mechanical test, but also for the ultrasonic wave speed, we didn't find that linear relationship between the two tests, so that we need a deeper analysis on the results to try to find that relationship between them. And that's it. Thank you.